Okay, good afternoon. Thank you for coming to our talk. We talk about crypto, but don't be scared. There's not, no equations, no scary stuff. So we're super happy to be here, Black Hack again. So very quickly about us, if you don't know us, we come from Switzerland. We work for a company called Skuleski Security, and we do crypto stuff. We do research, consulting, code review. So you might know me for some crypto stuff I did. I talked at Black Hat last year and DevCon Infiltrate. And I'm here with Jolan, who did his master's thesis with me. And it's his very first conference talk. So he's been doing a good job in his master's thesis. I'm sure he will do a good job today again. So it's a very small commercial plug. I read a book recently. The paper copy is not out yet, but you can order it on No Starch, which is an amazing editor, by the way. Okay, so today we've started about saying what does it mean to test cryptography. Cryptographic software, it's like software, but there are some particularities specific to crypto. And we'll present what we call differential fuzzing. So that's a term I introduced like maybe a year ago. It turned out a bit differently than what I expected, but I'll give you all the details. And then we'll present the tool that we are going to release today, that we actually just already released. I was a bit lazy, so I put it on GitHub like 1 hour ago. It's called CDF, for Crypto Differential Fuzzing. We'll tell you how it works, the kind of test it does, and we'll do a small demo before talking about the issues we found. So what does it mean to test cryptography? So like any piece of software, you want to test two things. You want to test functionality, meaning that when you send a valid input to your cipher or hash function or RSA, whatever, you want to get the valid output. So valid means conformant with the specification. And you want invalid inputs to be rejected. So you want your function to send you an exception or an error code so that the caller or the user can understand that something is going wrong and that there's an invalid input. So you also want to test the security of the software, obviously. So the program should not be abused by attackers. You should not have any, memory corruption or the usual stuff. And what is specific to crypto is that you want to avoid the leakage of secrets or of private keys, of plain text, this kind of thing. So it means not only leaks for example, memory dumps, but also leaks in terms of side channels, typically in terms of timing leaks. Okay. So what do you test against what? There's two basic cases. The first one, you test code against code. So let's say you have a baseline reference implementation of your cipher, and you want to create a new one, and maybe in a new language or with a different optimization target. So this is the ideal case, because you can have as many debug values as you want, as many test vectors as you want. And it's pretty easy to find the bugs in your implementation and to fix them. The second case is much harder. It's when you only have like a specification, a bunch of A4 documents, which tells you how it works, but many times it will not tell you like the internal and intermediate values. It will only give you a bunch of test vectors. And you have to fix and debug your own code until you match the test vectors. What's even harder is that sometimes the specs is not complete, it's not comprehensive. That sometimes happens in pay TV. It's very annoying. So today we're going to talk about the first case, code against code. Now about automation, automated testing. There's many types of tools. The simplest one is static analyzers, for example, the analyzers in Clang, which will report issues about your software security, but not about the correctness of the crypto, obviously. The test vectors, on the other hand, they will tell you whether or not your code is correct in terms of functionality, but it will not tell you if the software is secure, or if there's any bug or undefined behavior. Now you have maybe more advanced tools like what we call dumb fuzzing. For example, AFL is pretty smart, but it's still in the category of dumb fuzzers. It doesn't know what it's testing. It's just trying to be as smart as possible in order to maximize the code coverage. And it will typically look for crashes. So most people use AFL to look for crashes. You can look for other kinds of problems. So that's useful for crypto, but it will not help you in finding the pure crypto bugs. Now you have the smart fuzzing. So typically it's the kind of fuzzer that is aware of the API it's testing. For example, your fuzzer will know that it's testing, for example, a PKCS11 parser, or it's testing RSA or AP. So then they will know which kind of input to send to maximize the code coverage and to maximize the number of bugs found. And now the more powerful approach is verification, formal verification, which can, for example, prove mathematically that one implementation is functionally equivalent to one another, or it can also prove some security properties of your protocol. For example, it's been used to prove the forward secrecy and other properties of the WireGuard VPN software. So another question is, how to maximize the efficiency. Static analyzers are pretty easy to use, but not so powerful, and formal verification is very powerful, but very hard to use. So in terms of Pareto efficiency, you have the red area here where you have smart fuzzing and formal verification. The test vectors is much lower on the curve. So we'd like to be at the level of the question mark, get a good return on investment. Moreover, the method I mentioned, they're not perfect. They will most of the time not check the quality of the randomness. So randomness is very important in crypto because if it's incorrect, then everything is insecure. They will most of the time not check for timing leaks. You have some Valgrind plugins that try to do this, but it's a very special case. And like I said, the test vectors, most of the time you get test vectors for the valid inputs, not for the invalid ones. Okay. And they will only look at, for example, the default version, for example, RSA 2K, but not all the possible versions of RSA. All right. So how to do better with a new tool specific to crypto implementations? So what we call differential fuzzing is not very new. It's just the idea of comparing two implementations, but in a kind of automatic way. Several people have done this before. For example, Solar Designer tried to test his new implementation of MD4 by comparing it to, I think, the OpenSL version. Frank from Lipsodium did something similar. But in these two cases, they were only specific to their own tool, to their own software. So we want to make something that's generic, that not only us can use, but that anyone can use in their own software. Something that is agnostic of the language, of the API, and of the platform. Okay. So to give you a concrete idea of what it does is pretty stupid. Let's say you want to test hash function. So hash function in crypto, it's a black box, something that takes an input of arbitrary size. It can be 1 bit, it can be 1 gigabyte, and it will get you a small output of, let's say, 256 bits, which should look random to be secure. So now you have first program P1, which is a hash function, for example, I know SHA-2, and you have P2, which is another implementation of SHA-2. So the program, your fuzzer, will try to generate as many inputs as possible that maximize the cut coverage for your hash function, and they will check that P1 of X is equal of P2 of X, that for the same input you get the same output. That's pretty stupid. It's a bit less stupid for encryption. So here the input generation is not just a message, it's a message plus a public key plus a private key that matches the public key. So P1 and P2 in this case are not doing the same thing. P1 is encrypting the input X, and P2 will decrypt. So you encrypt using the public key and you decrypt using the private key. And at the end, you want to check that after decrypting the ciphertext, you get the same input that you started with. So for signature, it's pretty much similar. You get a message, and at the end, you want to check that your signature on this message is valid. Okay. And now let's talk about our new tool.
All right, so CDF is a tool we developed to use that approach of testing. So we wanted to do crypto differential fuzzing. So we decided to implement it in a way which was completely able to test executable in a black box fashion. So no instrumenting, no compiling, no nothing. You just get an executable. So we did it in Go. So we got the CDF executable, which can support many tests at once, concurrently, and which is completely language agnostic, as GP said. And we can test Go code, C code, Python code, Java code, whatever with it. So the bottleneck won't be our tool. It will always be the tested implementation, because those are the ones doing the actual computations. GP started working on CDF in May, and I arrived in September, and we mostly finished the software in March. So why would you use CDF? Well, CDF will do differential fuzzing on the implementation you got, but it won't test just functionality. It will test functionality through the differential fuzzing approach, but it will also do a bit more. So we decided to also test correctness and security of the implementation through unit tests. So we got a bunch of unit tests which will be run against both implementation, and you can compare the outcome for both. So we check for insecure parameters, non-compliance with standards, and other edge cases which are interesting. So we won't replace formal verification at all. It's really not the goal. The goal is to replace unit tests and do a bit more than unit tests. And it will also test interoperability since it's differential. So you've certainly heard of another project which is about unit testing. It's switch-proof by a team of researchers at Google. They got really nice unit tests for the Java Common Crypto Interface, and they found a lot of bugs. So that's a really interesting approach, and it's completely complementary to ours. So we could typically take their unit tests and run them in a differential way against the implementation we test. We do not yet, but we typically plan to do that later. So yeah, really interesting project. So how does CDF work? So say you want to test ECDSA. You've got OpenSSL, EmbedTLS, Bouncy Castle, a lot of libraries implementing ECDSA. And what you want to do is testing your implementation against one of those. But those won't have the same API. We don't have a common crypto API for all libraries. It's not standardized yet. It's a shame, but that's the case. So how do you deal with that? We decided to deal with that through what we call interfaces. So for example, if you want to test an ECDSA program, you will have to, ECDSA implementation, you will have to code a little program which will work as a proxy between your API and our API. So currently our API is only on command line arguments, so CDF will basically be doing exec calls on the implementation at hand with the arguments in command line. So for example, for ECDSA, if you want to sign something, you will just need to get the public key coordinates X and Y, the private key D, and the message. And your program should output the signature R and S. If your program does just that, then you can use CDF to test it, which is really easy to code. So for example, in Python, it's like 35 lines of code to do a proxy between a cryptography.io library. And
here you might ask the question, why do we need the public key for signing? Because in some implementations, they need not only the private key, but they need more stuff than what they actually need. So we need to be as flexible as possible to support as many implementations as possible.
Yeah, exactly. So sometimes to implement, to get a private key, you need the public key in the private key. It depends on the API. So yeah. So the CDF interface are really generic APIs in command line. We will do something more AFL-like later with file-based APIs, but it's not there yet. It's completely black box, so you don't need to instrument your executables. And yeah, it's really silly, the interfaces. They won't do anything fancy. So for example, there you've got CDF on top. That's the binary or program, and it will try to communicate with your library on the bottom through the proxy interface programs. So if you get, I don't know, an OpenSSL implementation, you make a little program to just proxy the OpenSSL API calls to our API, and you do the same for yours, and you can compare them. It's really easy. So there is an example that's the full code of the proxy program for ECDSA in Python. 35 lines of code, it's really quick. But you can test a lot of features with just that. That's the same for Go, so it's a bit longer because actually there we support one more additional flag. It's a detail, you can read you can read it on the GitHub page later if you want. But yeah, and in OpenSSL you've got all the pointers, you need to clear stuff, so it's a bit more line of code, but it's still fairly easy. So now,
okay, so very few examples of that. Again, there's nothing complicated. We try to be as simple as possible here. You can check all the details in our code. So again, the simplest case is that of a hash function or a keyed hash function. So a keyed hash function is like a hash function, but you have a secret key, a secret parameter. So you can only compute the output if you know the secret key. So a PRF or pseudo-random hash function, pseudo-random function, or a MAC, they're essentially keyed hash function. So here, P1 and P2, they do exactly the same thing. So you're supposed to get the same output on the same input. So what we'll try to do is, in very simple, we send different inputs with different values, but with different sizes. For example, the empty input, or input very long, or some input that is aligned with the block size, or that is not aligned with the block size, this kind of thing. And sometimes we will find some specific behavior. For example, if you look at HMAC, HMAC, it supports different sizes of keys. So let's say you have the key 1, 2, 3 with the byte 1, the byte 2, and the byte 3, and you have the key 1, 2, 3, 0, then these two keys will behave identically. You will get the same output for the same input, even though the keys have different sizes. It's not a bug as a feature, but you should know that it works like this. It's not ideal, it's not insecure, but if I were to design a new Mac, I would not do it like this. For ECDSA, again, without all the details, so here, as we've seen, is different. The first program will sign, will issue a signature, and the second one will verify the signature. So if you create a legit signature, then it should be verified successfully by the verifier. So then we will, in some libraries, sometimes you will give them, they will accept a message, and the function ECDSA sign whatever, they will take this message of any size, they will hash it, they will get the hash value, and they will sign this hash value. In some other libraries, do it a bit differently. They accept a hash, and they sign the hash. So they will not hash the message for you. But sometimes, if you give them something larger than the hash, they will just truncate it and take the first 32 bytes or so, and sign this, ignoring the rest. So ideally, it would be nice if they tell you, oh, you sent me something that's too long, I need to ignore the last bytes. But not all libraries do this. We'll also check, for the very abnormal degenerate cases, things that should not happen and that are insecure. For example, if the public key is 0. So if your public key, if your elliptic curve point is 0, then bad things can happen. If the private key is 0 as well, or if the hash function or if the hash value or message that you send is 0, then what happens? So I'm not going to the details, but you can guess what can go wrong here. So here you don't need to look at the code, let alone understand it, but it's just to show an example of test that we do for ECDSA. So here the name of the function is test infinite loop here. So it tests whether your ECDSA signing function will enter an infinite loop if you send special weird parameters. Okay. Now for RSA, so we've been talking about ECDSA, which is signature algorithm. Then RSA encryption will encrypt, obviously. So again, here P1 encrypts and P2 decrypts. We'll try different size of messages. And actually in RSA, you can have different size of modulus, which is essentially proportional to the size of the message. To sign, you raise a number to the power of the public exponent. So the public exponent, it should normally be small, so that the encryption is faster. But the decryption exponent, which is usually denoted D, it should be very large because it should be a value totally unpredictable. So normally you should not have a big E, you should not have a big public exponent, you should not have a small D. If your D is very small, then something's definitely wrong. So you can test whether or not your library will do this check or not. And you can also see what happens if you send a message bigger than what the function expects. Okay. What we're also trying to do, detect timing leaks, but we're talking about this in this slide. So timing leaks, it's very hard to detect because it's usually how much time you allow to test to find a signal. So we did not reinvent the wheel. There's a very nice piece of software called Dudect by Oscar Repara and his colleagues. I think it's written in C, right? And we just ported it in Go to integrate it in CDF. It's very powerful. We were able to use it to find leaks of a few nanoseconds. And well, the upshot there was that, oh, we have a timing leak. Oh, that's great. Then let's try to exploit it. And we found out to exploit it, we needed way too many samples. But still, we found that there was some actual timing leak. Now, demo time. So, first time we do the demo, hope it works. Okay, let's hit play. Let's try to hide this thing. Okay.
All right, so there.
Okay, you can comment on this.
Yeah, what happened there is that in the first part, we tested the ECDSA interface, so we specified its ECDSA. So CDF is aware of what it's testing, so it can't use undefined interface. So there we tested it against CryptoPP and Embed TLS. And as you can see, nothing wrong. If you send a 0 private key, both are rejecting it with an error. And if
it was fast in this case.
It went really fast actually.
But we can see the next example.
It is really fast.
Okay, let me hit play now.
And now if you try again with Embed TLS now, yeah.
Okay,
there you can see something fishy is going on.
Where was it?
So what happened is that the Embed TLS implementation accepted the 0 private key as a valid key and signed the message without any error. So that's really bad because the resulting signature won't be secure at all. So
okay,
yeah.
Let's continue. Okay.
So if we go on, we can test something else. So it's really interesting. If you try the OpenSSL and Embed TLS ECDSA implementation and you try to provide the hashes directly, so it's not a message anymore, they won't do the hashing, they will directly take the hashes you are providing. What happens is that if you get a 0 valued hash, Embed TLS won't sign it because it's a 0 value, so it's completely, screwing the multiplication, but OpenSSL will accept to sign.
We're not trying to do OpenSSL bashing here.
No, not at all, yeah. So that's an interesting case.
No, RSA.
And also there what we can see is that Embed TLS didn't run into an infinite loop, but OpenSSL actually did run into an infinite loop upon malformed parameters. So that means you can DOS OpenSSL if you can provide the parameters. So that's not something which should happen, but who knows? No, yeah, if we try again against RSA, OAP, nothing wrong there. If we try with the Go one, what you can see there is that the Go implementation won't accept a larger exponent than 32 bits. So that means it's an integer, but that's actually not a bug, it's a feature because the Go team decided they didn't want it to have too big public integers because it's bad for performances, it's not really good for security and so on. So they explicitly made it an integer, so you can't use big hints as exponents there.
So one lesson here is that many APIs don't behave consistently. Sometimes they would be very conservative, and sometimes they would be very lax in what kind of input they accept.
Yeah, so both libraries are not interoperable in that regards, by the way. So if you have a big int exponent, you won't be able to use a Go implementation to do whatsoever you want to do. And now we are testing timing leaks there. So timing leaks, sorry?
It takes 10 minutes to complete.
Yeah, timing leaks are really expensive to test because you need to do thousands of traces to get reliable statistics. So that's really slow, but you get results and you can see that's not really meaningful to you, I guess, but those are metrics, and if we get past a certain point, like 5 for the max tau value, for the max t value, then that means you really got a timing leak. If you get 1.8, like you get there, maybe not, maybe yes. So you have to run it for way longer to actually get anything meaningful.
Okay, issues found.
So yeah, what kind of issues did we found? So here you can see we tested OAP, ECDSA, and DSA on multiple largely used libraries. And for DSA, it's really bad. I mean, most libraries are not testing domain parameters, they are not testing the boundaries, they are not testing a lot of stuff, so you can provide invalid parameters and do crazy stuff like remote DOS, the signer upon invalid parameters. Crypto PP was really good in that regard. We weren't able to fault it. It doesn't mean it's better or worse than the other. It's just
maybe a small warning to people in the audience. It doesn't mean that Go crypto sucks. It just means that they made some design choices. Where the consequence is that they try to accept parameters that they should not accept. I mean, crypto++ fares pretty well here because they're paranoid. But as you see, Go they fix some stuff that we did.
Yeah, so we reported some of the problems. So for example, for a DSA, as you can see here, if you provide invalid parameters to the signer, it can fall in infinite loops, or it can provide always valid signatures, which is something completely silly. I mean, if the signature is valid for any message, why would you sign it? I mean, why would you want it? So here is a picture from the standard, the DSS, so digital signature standard, which is saying basically that prior to signing, you should obtain assurance of domain parameter validity. So that's clearly stated in the standard, and that's also true upon verification. Prior to verifying anything, you should obtain assurance of domain parameter validity, otherwise you can't assure anything, you can't validate the signatures. So not all libraries are doing that. For example, here, this is the signing process for DSA. It's somewhat summarized, but basically you will generate a random k value between 1 and q. You will compute r, which is the generator k to the g to the k mod p mod q, and if r is 0, then no luck, you get a k which is a multiple of q, for example. So you just pick another k, and the probability of getting another one, which is again a multiple of q, is very low, so it shouldn't be 0 again, but if it's 0 again, you retry. But that's a problem if g is 0, for example. If g is 0, you can make 0 to whatever you want, it will get 0 most of the time, I mean, always. So you get an infinite loop there. So it's explicitly stated in the standard that the generator shouldn't be 0, but what if it is? Well, some libraries, Go and OpenSSL, for instance, won't check that, so we reported the problem to both. This is the Go implementation. It's a for loop which will always generate a new k as long as r is 0. So they fixed the problem by limiting the number of attempts. So if you make more than 10 attempts, then it's not a valid parameter. That's a good detection, but that's not the best fix because you are not checking the domain parameters, you are just mitigating the problem. So we also were able to confirm a timing leak in RSA OAP thanks to the Dudect implementation, and that's a bad thing because RSA OAP, if you get timing leaks, you can get timing attacks, and you can basically decrypt the message using oracle decrypt, timing oracles. But
maybe the attack is not as well known as the Blashenbacher attack on PKC 1.5. It's just a ciphertext attack, but it's extremely powerful in the sense that just by using timing leaks, you can...
Yeah, exactly. So Munger's attack, it's called. It's really powerful, and we actually implemented it in Go, the Munger's attack. So if you want to play with it, you can too. And we were not able to use it against the RSA implementation because the noise of the operating system is so big and the signal is so low that you need really too many traces to do any attack there. So generally, we observe that most crypto libraries are really concerned about practical attacks, practical problems, but they won't really care about, domain parameters, boundaries, and such details. So if you can't prove that it's a practical attack, they might not fix it or might be reluctant to do it. But it's sad because it's not a good defense in depth. So most of them support weak parameters, they won't strictly conform, and not a good state.
Okay. Now it's already time to conclude. We have time for questions. So to summarize, we have this new tool, CDF. It tests correctness and security of crypto software. It's only for crypto stuff. It's in Go because Go is quite nice language, straightforward to cross-compile and portable. And we rely on this approach of comparing the behavior of different implementations. So you have, maybe you need to have an implementation you trust in the first place, or maybe two implementations that you don't trust so well, but you just want to see, how differently they behave, or just see if they can, work together. And we found a couple issues, not so many, but we focused on what we believe to be the most secure libraries and the most widely used features. So we not look for the low-hanging fruits, but instead for the hardest ones. So there's still a lot more work to be done. We need more interfaces. In other words, we need to be able to test more stuff. Because we don't even test Diffie-Hellman or CDH, which is used everywhere. We need to do more tests. So if you look at Google's tools, they do many more tests than we do, but they don't do this in a differential way. And again, we need to test more libraries. We just looked at maybe 4 or 5 different ones, the one that are actually the most used ones, but maybe you want to test your own stuff. Okay. And also we want to, test our own software because there's probably a lot of bugs that crept in. So so you can find CDF at this address on GitHub, Quick Security, CDF. And if you have any question, you can post it in the issue tracker. We're happy to take pull requests. And come to us if you have any comment. Okay. Thank you.
So questions maybe? No. Yeah, go to the mic.
Sorry.
So is this designed just to test crypto primitives? Like, would you use this to test an arbitrary protocol that, you might make up yourself for your particular application?
We don't support TLS 1.3 yet, and it would be way more complicated. One of the reasons is that we're completely stateless. For example, if you want to test hash function, you will call the function once, you cannot use the update, finish. And for testing, for example, a more complex protocol like TLS, for instance, you would need something more complex to do some useful test while being stateless. We can turn it into a stateful system, but it would be a lot more work.
So as we should basically use your results rather than your software in particular, right?
Second?
Because you wouldn't. I would never actually implement my own ECDSA from scratch.
Yeah.
Right?
So
I should only see your results to see which one implements it better.
Yeah. So you observe that if you don't implement your own crypto, which I don't recommend that you do if you don't have to, then the results of our tool can indeed be useful to get an idea of how these operations, how these libraries behave, and what security they do provide.
Thank you.
Yeah. You mentioned that the DSA standard says you should test the parameters of DSA.
Yeah.
Is it specific about what to test? Because this parameter testing is kind of a tricky issue. For example, I know one of the numbers in the DSA parameters is a prime, and you can test whether it's a prime. But that's pretty expensive to do during a signature operation. It's similar with Diffie-Hellman. In Diffie-Hellman, you have these parameters from the server in TLS, and you could, in theory, test them, but it would be really slow to do that. So
testing if it's safe prime or.
Well, that's true that some tests can be expensive, but what you need to do is obtain assurance once that the key is secure. Once you've got it, you can sign as many messages as you want. So you can just, if you are maintaining a library doing that, you can just imagine, for example, adding a function to test the validity of the key. And once you've got the function, the user must call it when he needs it, but it doesn't need to be at each signature. So.
Yeah, but I can tell you that, for example, a browser would never implement a test that would take 1 second before you can make a connection.
Yeah, that's called a trade-off. Yeah.
Yeah, that's true. But DSA is hopefully no longer in browsers. So
But if your Hellman is, then it's basically
yeah, sure.
I mean, my question's sort of, I'm in the middle here.
Yeah.
Hey, JP.
Yeah.
It's sort of like that first question, but I unfortunately am in a position where I need to implement some of my own crypto for SRP. And while I understand you're not doing a whole protocol keeping state, the individual components of it, and I'm just wondering, well, I'm hoping you already have that in there, but I'm guessing you don't. And in a sense, how easy is it to add new things to test?
Yeah, that's a good question. Actually, we built CDF in a completely modular way, so you really can add new interfaces, new tests really easily. So yeah, that's a good question.
Great, thank you. I need this.
You need to write some Go code. But,
Yeah, it's in Go, but
yeah, that's one of the reasons we picked Go and not CPP or Rust, because it's generally perceived as easier to code for cryptographers who are not very good developers usually. Yes, if there's no more questions, then thank you guys, and yeah, we'll give this talk again at B-Sides in 1 hour, so if you like it. Okay, thank you.